All right, let me get started. So the next, as I mentioned last time, the next 4 lectures are basically about the design methodology and all the steps of the design methodology. There's actually 5 lectures, but we have 4 times to meet. So I'm going to try to prune them to kind of fit things into the right amount of time. I may skip over slides here and there to make things fit. Now, in terms of announcements, no, I don't have the midterm 2 graded yet. We just got the scans yesterday afternoon. They take several days to scan them for us. So I hope to have them maybe by the end of the week or this weekend. That's kind of the goal. For homework 6 and 7, I've had quite a few people ask, is this project okay? Is this project okay? Feel free to send me an email and ask. I will answer you. There's corner cases. The common things I've had are, is my 100 project okay? Yes. Is my 125 project okay? Yes. Don't use, like I mentioned in 125, don't use the clock dividers and stuff. For 125, same thing. Some of the code might be FPGA specific, and so you need to change it enough that it fits into tiny tape out. I also had people ask, who's in neuromorphic computing? There's another class, neuromorphic computing in EE. They're doing a tiny tape out as well. You're free to double count. I don't have a problem with that. So it'll be interesting project. So other questions about homework 6, 7, or the remainder of the quarter logistics? Oh, and then the last thing, I sent the new exam room for the final exam. It is not the same as the previous room, and they are not the same people as the previous exam. So everyone should have received an invitation to the exam. You're either in this room, which is like 2/3 of the people, or 1/3 of the people are in the other room. And we'll do the same deal. It's closer than, it's not in Baskin, but it's closer to here. So I'll make that announcement. Again, I made it online, I made it here. Show up to the correct location for your exam. Now any questions? Okay, good. Okay, so basically we're talking about the physical design now. So we're kind of skipping over synthesis, logic synthesis, because you do a lot of that in 125, except your target for 125 is an FPGA. We're going for an ASIC design and custom silicon in this class, right? One of the first steps is the placement step. It's basically where do I put all my logic gates and my macros and stuff in my design. Now what we're going to talk about today is I'm approaching this from the point of view that to be a good chip designer, you kind of have to understand a little bit what the tools are doing, because otherwise if you set parameters, you understand what those parameters affect and the results you get out. They're very limited in what they do because they're doing a very hard problem, and they will always behave kind of in odd ways. So what we're going to talk about is what makes a good placement versus a bad placement. We're going to talk about partitioning, which I think is one of the most interesting general CS algorithms you can have, partitioning things into 2 parts, like jobs, designs, whatever. It's an interesting algorithm, and it gets used for placement in one of the main placement techniques. And then I'll talk about the 3 types of placement algorithms from a high level that any commercial tool uses. And so this is going to be an FPGA placement tool, an ASIC placement tool. They all use some variant or combination of these. And then we'll talk about the parameters that are then in OpenLane, LibreLane. I forgot to switch LibreLane. Now, oops. And placement's a bit like Tetris. Tetris is basically your limited dimensional placement where you have things coming in one direction, you place them in there. That algorithm that you use in there is called a constructive placement algorithm, where you're basically adding things one at a time to get your final result. It's not good. This type of technique is not applicable to chip design because, first of all, determining what you add next is a hard problem. So what order do you pick them in to add? And second of all, that's just trying to get 100% density. So you have the rows disappear. It doesn't have wire length. And so you have to do things based on connectivity rather than just where things fit. So that's what makes it kind of a challenging problem compared to something like Tetris. But when you start thinking about placement, it gives you kind of nightmares if you kind of do a lot of Tetris and the similar problems. So how do we define the placement problem? Well, again, we're coming in with a set of cells and their complete information. So this is from our lib files where we have our pins and our area and our timing, all this stuff. And then we have the netlist, which is how those connect to form your design. So we call it a netlist because way back in the day, it was literally a list of every net in your design and what pins that net connects. That's the simplest format for connectivity for a design. And if you look into the details of the def file that you've seen, you may have seen or I've mentioned, that is literally a net list in one section. It lists your cells and it lists the nets and what they connect. And it's a text file, so you can actually go in there and see the format of what it does. The output then is a location for each cell. So XY location. Actually, it also can have orientation and rotation. So do I flip my cell? Do I flip it upside down? You can also have that information. But the simplest way to do it is just location for each cell. And then basically the goal, you want all of your cells to be placed in the chip. Usually placing them in there is actually quite easy, but the question is doing it well gets hard. You want to make sure that to the first order, nothing overlaps, because then you'll have BRC errors, right? You can't manufacture cell shapes that overlap that you don't want connected. So that's number 1 rule. The number 2 rule, you have to make sure that you can route it so that you can then fit wires in to connect everything, and then it also meets timing. So it gets more and more stringent with what requirements you need for placement. But the placement affects all of those. Yeah, and then the challenge is the number of cells is very large. We're talking millions of gates in a typical industry design. Your tiny tape outs are probably going to be a few hundred, maybe 1,000 cells. They'll run pretty quickly. But when you have difficult to route designs or tight timing, placement can also be very time consuming. But it also is what predominantly determines how good your design is the placement. Now, there's actually, I'm kind of lumping placement together, and there's several types of placement. On the right, top right, so just to pick a graphic kind of example image, this is where you have standard cells we've seen, they all have the same height, and they fit into rows. Okay, they can have different widths. Typically, we alternate VDD and ground, so the rows may flip vertically. But in many cases, you just want to place those standard cells into the set of rows. That's one case. Floor planning is another case of placement where you have things that are not the standard height cells. So you might have your SRAM macros, you might have hierarchy, so you have a pre-designed core that you're going to use in a top-level chip. You might have an analog block that someone laid out by hand. The layout's already available. These things aren't necessarily the height of a standard cell, and they don't fit in rows. So you may place these during the floor planning part, and then you may have standard cells, like in this case, around those blocks. These might be 2 SRAM blocks, and then you have rows over here to put the standard cells in. There's in the past, there is also data path placement, and it's kind of a fallen out of fashion type of placement because most of the tools don't do it these days. But if you know there's regularity in your design, like let's say you have an ALU. That ALU has an adder, and it has a 2's complement unit, and a mux, and then like a carry check or something. These types of things can actually be placed in a what's called a bit slice design. You basically have all of your bits coming in here, say bit 0 up to bit 3 in this case. And then you have the bit slice being, here's your adder that operates on it. And then you have all your different stages of an ALU or something going in this direction. For signal processing, ALUs, certain machine learning, those types of placements can actually be useful. The problem is that most commercial tools don't do that. They just do kind of a sea of gates placement methodology, like an upper right, where you just have standard cells, you put them in the rows. I think that's actually a research area that's ripe for kind of investigation these days. Is how, and I have one of my grad students looking at that, like how do we revisit data path placement in the age of machine learning accelerators, right? But again, most tools you don't do that, and you just opt for basically either pure standard cell or kind of floor planning with standard cells. For your tiny tape-out designs, it's going to almost certainly be just standard cells. So I don't expect, I think one other person was talking about a custom thing, but most likely people won't do that. When you look at real designs, so this is actually, I think this is King's Encounter. I forget, it's an old image. But I've also shown you kind of the GUI for OpenRoad. They all generally look the same, just like we did layout. You have layers, you can turn on and off, you can look at different things. Here you can basically see 2 examples of floor plans. Both of them used placement of the macros. You can see the dark areas are actually macros. Like this thing right here is a block, a macro block. And this example has probably 50 or 60 macro blocks in a design. Those are all little SRAMs and things like that. If you have like a TLB or a FIFO, whatever, every one of those things has a macro block associated with it for the memory. And then you can see the highlighted things are basically the hierarchy of your design. So you may have the red stuff here. That might be a module in your design, in your Verilog. And the difference between the left and the right is sometimes you can turn on something that's called region assignment, where you can say, oh, even though I'm going to do standard cell placement, I want all of this module in this region. It's kind of a soft floor plan, if you will. Put everything here, keep them grouped together. On the right, it's more of a freeform placement, which is the default for most tools, where you can see that it'll still place the red stuff together, but it'll kind of flow into the adjacent logic and mix up different modules. So in most placements, you do the thing on the right, and you can see that things will get placed where it's convenient for them. What I mean by that, if something's connected to a memory block, it's going to get placed near that memory block. If it's connected to 2 things, it's going to be placed kind of between the 2 things. Or if it's connected off chip, it's going to be placed near that side of the chip. So it's going to try to group things in areas that make sense. Yeah.
I noticed on the right that a lot of the colors are still near where they are in the manual
Yeah.
plan. Is that because that's the most efficient way, or is that in preset a region where you want to be near?
So this is why they are kind of grouped generally. If you look at modern, at any design, even without supplying it soft constraints, you're going to see things kind of grouped like that. Because if you think about how you make a design, if you have a module, it's things that are connected.
Or what I meant was that it's like the red chunk is on the middle left.
Oh.
Is that because just like that's how the design is best done and designers do that, or is that something that could
So I guess the question is, how did they come up with the regions? Or the answer to this example, I don't know. I think this is meant to illustrate that placing things in strict regions is not the best way. You'll get a better result if you let things bleed, like on the right side. Now, when you do the, I won't actually talk about floor planning more than this, but one thing you can do in one of the floor planning problems is you can treat like that red area as a variable aspect ratio rectangle. And you can kind of intermix it with the other blocks and try to do block packing in 2D like Tetris to define where the best place is for that soft block. I'm not going to talk about those tools. In reality, most people don't use them in industry because just pre-placing your hard blocks and then doing standard cell placement scales to millions of cells, and you get the better results by doing that rather than the stuff on the right. That's partially true. OpenRoad does have a thing called was it RTL MP, RTL macro place that tries to do this. But if you look at the final results, it has varying levels of success. It's more of a research paper than something that's really tested and fleshed out. Now, so instead of the idea of these regions and how to place the blocks, which again is a very interesting thing, I'm going to mostly focus on the standard cell part of the placement, because that's my advice is if you have macros and stuff, you're best off by placing them manually. You know where they should be connected and so on. And unless there's many of them, you may have it make a pass and then iteratively improve it as a designer. But I'm going to skip over that floor plan part and just focus on the cell placement, which is what you'll spend most of your time with. Now, like placement, and also in routing, you're going to find that we do 2 phases of this, where there's a global phase that ignores some of the constraints, and then a detail phase. And in this case, the global placement basically divides the chip area, even though there's rows in here. It divides it up into areas, and we just put cells in an area, kind of abstractly, rather than a particular row in a particular location. So you can see this example, we might divide the chip up into a 3x3 set of 9 global bins, and then the objective becomes take my standard cells, divide them into 9 partitions, and put each of them into those areas, and then just put the cells in the middle of the area. Now, we know that they're overlapping, which isn't allowed, but we do it in a way that we know that those cells, the total of the area of those cells is less than the area of the region, because then they can fit. But we just don't worry about the detail of where they're at yet. And the idea of this is that you can do a lot more optimization if there's only 9 locations for things, rather than if there's an infinite continuous region of where you can place things. So it makes it a discrete optimization problem at this phase, which can be much better. And so that's why this closely resembles partitioning, which is one of the most interesting problems I mentioned. And then after this, you may go to detailed placement, which is then let's actually place the things into rows. And this example here shows an example of placement where there's actually space between the rows. All the examples I've showed you in this class actually have rows basically directly adjacent to each other. Directly adjacent is the modern way. If you have a lot of routing layers, that's the preferred way. In technologies where you only have like 3 layers of metal, these are kind of older than the one used in this class, you do what's called a variable row placement. And the idea is that you can actually use these regions between here to route signals. Right? You can do something like this to connect things between the rows. So that's only when you have very few metal layers, and basically no one does that anymore in placement. Actually, I won't say no one. I've seen a couple cases. One case was, who's seen things with like flexible electronics? In that case, you might have, if you can actually do like organic transistors on a flexible membrane, you often have only a couple layers. And if you do something like this, you would use that type of methodology. But in general, we don't do that. So what we essentially do that is, this is the same set of bins as in the previous example, except we divide it and everything has to go into the exact rows. So that's the legalized thing. And then the output of that is a non-overlapping placement, and so we have no DRCers. And remember, we made the standard cells so that we can put them in any row adjacent to any other cell, and they'll be DRC clean. So we can pack them together. You may want to leave space for routing even within a row, but we know that it'll be DRC clean if we do that. Now, if we pack it in there, is this a good placement or not? Well, it's kind of easy to see what a good placement and bad placement might be when we think about routing. This is the first problem, and you'll see things like this. The placement on the left is a bad placement. It looks like Jackson Pollock, the painter, where you kind of drop stuff on the paint, it's just everywhere. And then the one on the right is a nice clean, maybe it's an Andy Warhol, right? Everything's kind of organized and so on. The one on the left, you see the rat's nest. That means a lot of the routes are going to overlap. It's going to be very challenging to route. And one of the metrics we're going to see is congestion for routing. We're going to see a lot of congestion in that design. It may not even be possible to connect everything. Another example of this is you can see, it's things that are connected to each other are not near each other. Another thing is also, if you look at these I/O pins, this had a bad floor plan where the I/Os were just all put over in this corner, even though they're connected to things throughout my chip. That's a bad I/O placement. I actually, this last Friday, I spent basically about half my day debugging some I/O placements on designs for this benchmark suite I'm making. That really affects your design because it not only affects what it's connected to, but when you do placement, things connected to those I/Os want to be placed near the I/Os, and this means everything wants to be placed in that lower left corner. So the one on the right then spreads things out. Now, how do you spread them out? Well, the tools can do it automatically. They'll try to make a guess. They won't always make a good guess. Actually, I'll give you an example. In the design I had, it was this ML accelerator from Berkeley, this Gemini core. It had about 1,000 I/Os, and it actually meant that the perimeter of my chip was almost full with all of the memory interfaces. And so one of the things is I actually had it put the bits in order on the sides to actually make things line up. Think about the data path placement I just showed. If you put the bits in order, it's going to kind of seed it so that all the stuff connected to those bits are in order next to it and make a more regular placement overall. So I actually spent my time writing a Tcl script and actually having an LLM help me write a Tcl script to put them in order so that I have a better placement. And it got a very good result when I did that. Yes?
In PCB design, I know that there's talk about, if you have a bus of traces, they all have to be about the same length so that the delay matches up. How do you do that here?
That's a good question. PC board design with buses, you try to match lengths. In ASIC design, you don't care really. What's going to happen in ASIC design, you're going to run static timing, and that's going to account for your delays. So you're going to basically be limited by your worst one, and you're going to optimize that with either buffering or sizing or rerouting and so on. That's a very good question. I think in a lot of board design, you also want to match the lengths for higher order effects like reflections and stuff. The inductance of these wires is fairly small relative to the frequency, and so that doesn't affect them that much. That's another reason. So you don't really care about matching lengths too much, except maybe in the clock network, but that's an exception. Yeah, so good and bad placements. So it's kind of easy to see. So what are some of the metrics? So we've already talked about a few. The first number one metrics are area and overlap. Any extra space is wasted area. If there's not something doing logic there, it's essentially blank. So you want to minimize space between cells, but you want it to be routable. So you might have to leave space for routing. Overlap, that's a requirement. To be DRC clean, it can't overlap. Now, another metric is wire length is actually very hard to quantify. Like looking at this, you can say, oh, the one on the left, you have more crossovers, that's worse. Well, that's still hard to quantify. There is going to be a way to do that, but first I want to introduce a couple things that are kind of proxy metrics for placement. And the first one is called wire length optimization. And the idea here is a good placement will have low total wire length. So if I just take all my wires and I say how long each wire has to be, that's the wire length of my design. Less length means there's fewer routes, and so you have a better placement. Is that totally right? No. But in terms of delay, less wire length is better. In terms of power, less wire length is better. And I'm going to talk about congestion. That's how the demand of area for routing. Less wire length is also better. But it's not really always true. There's reasons you may not want to minimize wire length. This example shows kind of a trivial example with 8 cells placed into 4 bins, so global placement of these. The one on the right actually shows the minimum wire length placement, right? Because those 4 cells, only 2 wires cross from one bin to the other bin, right? So in this case, this wire length is small. Whereas over here, this wire length is bigger, but you have one cell in each bin, so each one of these wires has to go between each bin to connect each cell. The one on the bottom left might be better because it minimizes congestion. And what is congestion? It's basically if you take any boundary, say here, and you have things that want to connect on each side of the boundary, how many things can you connect? Now you have to use wires. How many wires can you route from one side to the other side? Well, there's 2 components of this. One, how many metal layers do you have, right? You typically use every other one to go horizontal. So if you have 12 metal layers, you might have 6 that go horizontal. So that means you have 6 metal layers you can do. How many wires can you fit on each metal layer? Well, given the length of that boundary, you know the spacing of the wires, which will give you the number of tracks of wires. You can find the discrete number of wires that can cross that boundary. That's the potential number of wires. And then on top of that, you have the number of connections you actually want to make. That's the desired number of wires. Much like we have slack in static timing, where you have your required time minus your arrival time, congestion is your available wiring resources minus your demand of wiring resources, right? You can fit so many wires, and you need to route so many wires across this region. If it's negative, that means it's like timing, you don't meet timing. In this case, if it's negative, that means you want to route more wires than you can. So you can't fit that many wires. And that's the definition of congestion, really. Is if it's a negative slack, or the demand minus supply is negative, that means you cannot fit them at all. In general, you have to be more relaxed than that because you may not be able to use every possible track. So there's also a soft limit as well that says don't go beyond some other number. So congestion is something we'll talk about and we'll look at a little bit more. Now, how do we actually figure out what these wires are? There's also different ways of computing the wire length. And the reason there are different ones is they're faster or slower to compute. The simplest one used in a lot of placement algorithms is over here on the right. This is called half perimeter wire length. Half perimeter wire length. What do I mean by half perimeter wire length? You take a box, you fit all the things that need to be connected together. So if you want to connect together these 4 pins represented by dots, you draw a box around it, and then you add together the width and height of this. So it equals width plus height. And that's an approximation for how long of a wire you need to connect those together. Is it exactly right? No. Is it fast to compute? Yes. So most placement algorithms, every tool will use half perimeter wire length during early placement. Because you don't actually want to route the wire. That's expensive and time consuming. So you basically use the location of where it wants to go and just do simple geometry to come up with the estimate. There are more accurate estimates. A star model, for example, you basically pick the median location or the mean location and have everyone route to there. That's a little bit better estimate in some cases than the half perimeter wire length, but it's also wrong in other cases. If you have a very high fan-out net, it's actually very far off from the routed wire length. If you have a low fan-out net, it's actually pretty accurate. Think about a fan-out of 2, it's just point-to-point, single line. Fan-out of 3, it's just the median and so on. The 2 on the right are the rectilinear minimal spanning tree and the rectilinear Steiner tree. So what are these? This is basically snapping to horizontal and vertical wires. And you can see, basically this one is using L shapes in general to connect different pairs. And you can implement this as connecting, you have to basically pick 3 pairs to connect 4 pins to make a complete wire in this case. And you do that by picking the minimum set in some order to give you the minimum wire length. That's a combinatorial optimization problem, which is actually pretty fast. There are polynomial algorithms, I believe, for that. But it's still, when you're doing it for every wire during placement over and over again, it's slow. So it's not used typically. Now the one on the right is the rectilinear Steiner tree. And this is a case where this right here is what's called a Steiner point. And this is where you can add an extra intersection, essentially T intersections, or you can have a plus intersection too, where you can do that to make the wire length smaller than the spanning tree. That is a known NP-hard problem. So that actually can be very difficult to compute. By the way, Aaron, Hodder, and I, and my grad students, we had a paper on using machine learning to predict Steiner points based on training it on nets. We actually had that at a conference about almost 2 years ago now. But it was actually really accurate and very good. It made it very fast for routing. But still, it takes more time to fire up an inference engine to do this during routing, so you don't do it typically during placement. Now, so all of these get used at some point during the flow. During early placement, you'll use the half perimeter wire length, and then usually before you do routing, but when you're kind of optimizing your placement, you'll do a Steiner tree because you're doing more incremental optimization. And then you have a more accurate view of each wire's length. But you don't know the actual routing yet. So you don't know which layers it's on, if the wires can actually fit, is there congestion and so on. But we'll talk about routing later a little bit more. Now, you can see out here these are different routing examples shown on like a global placement. So if we have the bins and then the cells are in a bin, you can see that the half perimeter wire length on the left uses the bounding box model, and then the minimum spanning tree algorithm on the right will have a more accurate view of what it might be. But here's an example of, it might be better that this route goes over here instead of that direction. You don't know yet. That's an optimization that's done during routing. Now, what about congestion then? I mentioned what congestion is, and you can see if we have that same 4x4 global placement, we place these things, we can see that every edge that one of these goes over, we have, again, the supply of wires that can go over it based on the number of layers and the number of tracks, and then the number of wires that actually go over it in our routing model. And here you can see if there's a lot of wires that go over that region, that's going to be a congested region. And that means that we might not be able to route that. What we might end up having to do is take a detour in the routes later to actually connect things, which will then make our wire length estimation incorrect and makes routing harder. So wire length is kind of the first priority, minimize wire length, but then doing a summation of all of the edges in kind of this global placement grid and the overflow, which is how many excess wires cross a region compared to the supply, gives us an estimate of how hard it will be to route. But this is also difficult to compute during placement. So it takes time because remember, we're doing millions and millions of cells, and so it's computationally heavy. But as we refine a placement, we will consider it during later steps or kind of the middle steps towards our final placement. Now, there are concrete things you can do to fix congestion though. And I mentioned I spent half my day Friday kind of figuring out a design. There's things to look at that when you look at a design, you can look at a congestion report and it looks like a heat map. It'll show red in an area, and that means you have high congestion, lots of things want to go there. And if you just pass it to routing, it'll choke. Your router will run for a day, 2 days, even for a small design. So what you can do is you can look around what's happening around those areas, and there's generally a couple of things. And I would say that the number one thing is basically pins, macro pins, and I'm going to say or I/O pins. Now, think about it this way. If I have, let's say, a macro block, and then there's a bunch of rows like this next to it, what's going to happen is the congestion that my pins are in here, the number of wires coming from the blocks are going to have a hard time connecting to the macro block. So one thing you can do is you can basically convert this and add extra space there. So you can actually tell it, don't have my rows go all the way up to this macro block, but leave a gap. And this thing right here is called a halo. It's kind of a region around a block that says, don't put anything there, don't put any rows for my standard cells, leave it blank silicon. And the reason is then, you can use it for routing. If something comes in here, it can route down and over. This one can route over like this. And so it's extra routing space purely to connect the pins of the block. So that's one thing you can do to kind of do that. I mentioned the ordering of I/O pins. That can affect how many of these kind of up-down detours you have to take to route something. Dense pin areas. We showed the example with all the I/O pins in one area. That's a dense pin area. Another example is you could have a high net to cell ratio. And this is something we do see. And there's one case that I frequently see. It's if you synthesize a register file. So what is a register file? It's a bunch of flip-flops with like an address decode and a mux, right? It's highly connected because again, it's kind of like a data path, right? We have the rows where all the bits might line up, but it's not placing it as a data path because it doesn't know there's structure to it. It places it as a pile of cells with a lot of congestion. And so data path or register files have a very high net to cell ratio, a lot of connections and very few cells, so they're very, very challenging. I would say in this class, the most common reason people always say, oh, my computer's slow, it doesn't synthesize stuff. It might be true. Like a lot of people use big servers for this stuff, but the bigger reason is they'll take a design and just synthesize the whole thing, start placing and routing it, and ignore that it had a register file that should actually be a memory. And if you pull it out as a memory, it's placed as one block, not as 1,024 flip-flops with an address decoder and mux. So that complicates the design quite a bit. So my point here being, this is the type of stuff I was actually playing with my design. I spent half the day Friday trying to diagnose these things and also trying to see how well LLMs diagnose them. Right? I was doing exploratory stuff. LLMs don't know this. They don't. They look at this and what did it suggest to do every time it ran into congestion? Let's add more blank space. Let's decrease the utilization. Every time. It's like, I would actually had it down to like 25%. It's like, oh, maybe we should decrease it down to 15. I'm like, no. That's when I went in and I'm like, what's actually going on? And it was a combination of the IOs and some Halo sizing stuff. So, and actually one of the designs also had a register file. One of the benchmarks was a processor that I said any memory that was less than I think a few hundred bits, I said just synthesize it to flip-flops, and that was not a good choice. So, yeah.
When you say memory, you mean converting it to SRAM, right?
Yeah, to SRAM. When I say memory, I mean SRAM.
Okay, and then also, let's say for some reason you wanted to do it with flip-flops. Is there a way to sort of export this block of cells and tell it, these should be connected like this, write something that is more intelligent because it knows that there's like a repeating structure?
That's a very good question. So there are data path placement tools in industry, but they're difficult to set up and use. Tools are already difficult to set up and use, and I wouldn't recommend it. And you also have to buy another license. Every company wants to sell you more licenses to do more features. Remember, I also said how expensive the tools are. A data path placement tool is probably going to set you back 100K. So now, the other question is, are there things out there? Specifically in the open source area, there's a project that's actually pretty good. It's called DFFram. And this is basically a set of Python scripts that does exactly what you're saying. It says, oh, this is a register file. I'm going to place all my flip-flops. I'm going to place them in a perfect array. What it doesn't do is route them, though. It actually leaves the routing to the router later, but it says to connect everything in the structured way, which then makes it easier to route. That has to be called manually, though. There's no automated way of calling a DFFram module because it's made into a hierarchical block. Then you have to floor plan the block, and then you have to route things, and so on. So it's not really automated. But there is that open source project that you can use to do that. That would be useful. That type of addition in the open source tools would be useful, like to have people do stuff like that. Yeah.
Is this also applicable to other things where you have, it's not like a register file, but other cases of repeating logic? Like, for example, a GPU where you have 1,024 little processors doing the same thing?
Yeah, all of that is structured data path placement. And so I think you came in and I mentioned there is a data path placement, which is structured placement. In general, it's not I'm going to say it's not used in industry because of cost, more licenses, but also in many cases you get better results by just placing it as a sea of cells for other reasons. Like, for example, how big is your DFF array compared to the rest of your design? If it's 1,000 cells and you're placing 2 million cells, it doesn't matter that much. So it's kind of a ratio of how big it is. But I do have a grad student looking at this for ML accelerators because I agree in a lot of these designs today, there is a lot of structure and we're not leveraging that. So yeah, I absolutely agree with that. Now, yeah, so congestion, the key here is you've got to open up the design and look at it. I think it'd be interesting if I actually pointed the LLM at the congestion report. I might try this when I get back and actually tell it, look at the high congestion regions, find what cells were there, and see what types they are. This is the type of thing that LLMs are not good at, but you can give it the right keywords and it might be able to help you. But we're not there yet. Actually, there's companies trying to make tools like that and charging more license fees. So there's at least 3 or 4 LLM-driven chip design startups out there. Now, the other metric then is timing. I won't talk much about this, but we've already done a ton on static timing. You can run static timing after you do placement with the estimated wire lengths. Then you can use the half-parameter wire length, or you can use the Steiner wire length as a proxy for the actual routed wire lengths. And this gets done during our placement where you can make iterative improvements on it. The general way that the tools work is the main goal of all the algorithms is it tries to minimize wire length because the algorithms are very efficient at that simple metric. So what they do with timing then is they say, well, we're going to do wire length, but we're going to add a weight to different wires and say this wire is worth 10x more than that wire. And so you basically go through and find what your critical paths are in your design. It'll add weights to those to try to pull those wires to be shorter to make your critical paths faster. Now, it does that iteratively. It'll do a placement without any weights. See what your critical path is. It'll say, oh, add the weights on all these paths. Redo the placement. Now what's my critical path? If it guessed right and it got a good result, then you're done. If it guessed wrong and something else is critical now, you have to add weights on that, and you might have competition of one critical path for another with different placements. Yeah.
So how do you determine the weights and how do you determine where to place the weights?
So the placement algorithms will do that. The timing-driven placement algorithms will have different heuristics in doing that. There's a lot of research papers on how many paths to look at, how to change the weights over time as during the iterations. But this is the general approach that it does. But really, it's also a chicken and egg problem. Is you want to estimate the weights before you have placement, but you don't know the critical things until you do the placement. So it's like that's why they just repeat it. So do a placement, figure out the weights, repeat. Hopefully you converge. When you look at the placement results in OpenRoad, you can see it does like anywhere from 2 to 10 iterations of this during placement, depending on how tight your timing is. This is another example of if your timing is too tight, your placement's going to run forever trying to fix the timing. So you may want to look at this and say, how are my timing constraints right? If I'm one of the other designs I was working on, it had kind of a natural frequency if I didn't do any optimization of about 300 megahertz, but I was trying to synthesize it for 500. It spent a lot of time here trying to figure out what to do, like doing gate sizing and fixing placement and all this stuff. So one thing to look at then is how many critical paths do I have? Is there a problem? Do I need to redefine what my goal is? And this is the type of thing where unless you're a designer, you can wait for a day for something to finish. It's chugging away at something because you gave it the wrong setup, right? That's the important thing. Garbage in, garbage out. If you just naively say I'm using the same result as my last, or same setup as my last chip, that's probably the wrong answer, or it's maybe the wrong answer. So that's another example here. All right, let's talk about partitioning, and then we'll take a quick break for 5 minutes, and then I'll talk about the different placement approaches. So, okay, how much do I want to talk about this? I'm not going to talk about too much, but the point I want to make is when you divide a design, you want to divide it into the bins, into different locations. Generally, you want to do it so that you minimize what's called the cut size, which is the number of nets that pass from one bin to another. Because if you can put everything that's connected together in one bin, that's the best solution. But if you have something completely spread out, it's going to be a horrible solution. Think about back to the thing I showed at the very beginning with congestion. Here, if I basically divide this in half, and I look at the number of cut nets versus this, the one on the right has very few of these red connections going from left to right. That's the cut size of that placement. The one on the left has many, many nets going from left to right. So that's kind of a simple metric of measuring, is that a good placement or not, if I want to divide it into two things, two sets. So what does placement look like? If you have some network like this, you may want to divide it into 3 sets of bins. You might want them to be roughly equally sized. That's actually even harder partitioning problem to balance the partitions. But you may do it so that there's only 4 nets from the left block to the middle block and 4 nets from the middle block to the right block. That's kind of the ideal case. There's only 4 wires connecting those things, and all the other wires are kind of within the region of each of those blocks. So it's just meant as kind of an illustration of what does a cut size mean. It can be kind of abstract in that things in different partitions may not be related to each other, but they may be. Now, and the other thing is it can be different than your logical hierarchy. Your logical hierarchy, how you make your modules in Verilog, might be a good partition sometimes, but other times it's actually really bad. The reason it's bad is your size of modules is not uniform. You might have one module that has half of your chip, and another module that's just like your reset circuit. So the 2 modules are not the same size, and so they don't have the same weight. So, but logical hierarchy is easier to understand. So grouping things by what they're used for makes sense in that way. Yeah, so partitioning is different than the logical hierarchy, but logical hierarchy can be used to seed the partition sometimes. But they're definitely different problems. Okay, let's take 5 minutes, and then I'm going to talk about the placement algorithms. I know it's a little earlier to do a break, but I want to have a break. So 24, we'll be back. What?
Would you pass GDI as first try?
It might.
Why didn't you do anything with like PK or anything?
You might. The defaults might have worked. What is your design? What?
Daily.
Pretty simple.
So
So
I have applications vision.
I'm surprised then. Maybe. I don't know. I'd have to look at it. Yeah.
I haven't even fixed my stuff yet, but that's kind of confusing, because we're so limited on like the pins and like how extended to remind people.
To have a command that like loads an edge.
Okay. We're gonna get started again. So what I'm gonna talk about now is we kind of know the metrics for placement. So we want to do non-overlapping. We want to minimize wire length. We want to minimize timing. We want to minimize congestion. What are the general algorithms that we use to do it? And there's 3 types of algorithms that each have some benefits, some disadvantages when it comes to those different metrics. The first one, in the initial approach that people use for placement, was partitioning-based approaches. And basically, we saw in kind of the little examples I gave, if you divide the chip into areas and then assign things to those areas, you basically create a partition. But it tries to do this in a way that it's not, if you, in our example, we showed either a 3x3 or a 4x4. If you try to go from a design to a 9 partitions, that's actually quite hard. It's actually much easier to do what's called bipartitioning. So just divide it into 2. So the partitioning-based approaches tend to use bipartitioning, which can be solved much more efficiently, but you do recursive bipartitioning. So divide it into 2, now take each of those halves, divide them into 2. Now take each of those halves, divide them into 2. So you basically have a tree of these cuts until you get down to some region that's a reasonable region. And then every time you do a division, all of the circuits in one half are assigned to each partition. And then the metric of this is to minimize the cuts. Now, cuts are good. They're kind of like congestion, right? You have less things passing back and forth. They tend to help minimize wire length, but they don't. There are some issues with them. So I will say a lot of the I don't know which ones now, but a lot of the FPGA tools tend to use recursive bisection partitioners. Now let's look at an example. So here's kind of a circuit and then the final result, where on the final result you see that there's a number of cut lines. You can see they're slightly numbered. So this one right here is number 1. So the first thing it does is it cuts it into a left and right half. And it says, oh, I want all of those instances to be in the left and then the other ones to be in the right. And then I go through and I do a second cut, which is going to alternate directions. So in addition to kind of cutting the halves in half, it can say do a vertical cut and then the next one should be a horizontal cut. So you can see here, this is number 2, where it takes those 8 things and puts 4 in the upper quarter, and 4 in the lower quarter. Then you see cut number 3. Where's 3? Oh, 3 is the other half over here. So it does the right half. It divides it here. Let me do a different color just to be. So here's number 2, and then number 3. And then it goes through and it can do each of these ones. Here's 4, it cuts it into left and right. 5, it cuts this into left and right. 6, this left and right, this left and right, and so on. Until you may stop when either one cell per area or you have some small number of cells per area that fit. Okay? So that's the general idea of it. So you need one algorithm, divide it in 2. You want it to be roughly equal halves, but you want to minimize the cut. And then you assign it and repeat. So it's a fairly straightforward algorithm. Now, what algorithms are there? I would say even if you're not a chip designer, the first 2 of these are actually super useful algorithms that they're kind of like Code Academy type questions. They're simple algorithms. They're hard to get right. They're actually very hard to program, even though conceptually they're super simple, because they have very efficient data structures. They're iterative algorithms that run in polynomial time and get somewhat good results. Now there's other approaches. Network flow is something that's used as they can optimize things in a more mathematical way. Spectral partitioning kind of does multi-dimensional thing and then projects it. So it's a higher order math technique. But the one that actually gets used is quite simple is multi-level partitioning. And what this does is, I'll actually talk about it. I don't know if I want to go into detail on it. Most of the best placers use multi-level partitioning, which what this does is at your top level, for example, let's say you have 1 million things. Rather than dividing it into 500,000 and 500,000, let's form some groups first. So let's cluster things up and say, take the nearby things that are connected and make one cell out of it. It's actually 10. If we do that and say combine things down by a factor of 10, instead of 1 million cells, we have 100,000. Partition that. So 50K, 50K, and just you're basically pre-grouping things that want to be connected to make the partitioning easier. And then when you do that, you can go all the way down to the bottom like before. And when you go back, when you do a step where you basically unpartition those groups or ungroup those things and do a refinement at every level, which means you just swap things greedily to try to improve stuff. So by doing this kind of pre-clustering and then refinement as you go back up, you can get a much better result than the first 2 algorithms. But this actually can use these first 2 algorithms with that kind of clustering scheme. So I'm not going to talk about that in more detail, but now the bad part about it is you minimize cut size, but it doesn't really know about routing. And here's an example. Let's say we divide something into 2 halves, A and B, and then we do our next cut, which is vertical. A and B, you want to be both in the top halves. But if you're partitioning with your second cut, the second horizontal cuts, they could get placed where A is in the bottom half and B is in the top half. That's bad because now the connection between A and B goes across the whole chip rather than just one of those boundaries. So it's a little different than routing. It's still one cut, but it's going to correspond to a worse route. In other words, it's going to take an L route to have to route from A to the right and then up to B. Right? Your route's going to look like this. Whereas in this example, it's just a horizontal line, which will be much better. So the wire length of the one on the left will be more efficient, which is not captured accurately in the partitioning-based approach. So that's where they kind of, one of the reasons they are not good. Now, the pros and cons, they're very fast. The cons, they're not stable, meaning if I change one cell, I'm going to get a completely different result. So it's not predictable. Think about it this way. You change one line in your Verilog code, you rerun placement, completely different placement. It could be good, could be bad. You could keep doing it until you get the right result, but then you freeze your code, right? Because you don't want to change your placement. So that's a bad thing that way. Also, how to start partitions or where to kind of start doing it can FM and KL need you to start with an initial partition and you refine it, and how you start with the initial partition can affect the result too. Now, in addition to routing, timing is hard, but it can go back to the weighting metric. Like if you say, oh, this net is 10x more than that net, try to not cut it. It'll be the equivalent of cutting 10 nets. So you can try to do it with timing like that. But in general, those kind of cons are some significant drawbacks. So most tools will use, most non-FPGA tools, and actually probably a lot of FPGA tools now, will use something called analytical placement. And what they try to do here is they try to actually formulate the wire length as a cost function. And it's actually, if you have XY coordinates, you can compute the distance like the half perimeter wire length, right? You can compute the bounding box, you have the width and the height, each of those contribute to the wire length. And then we're going to try to form this as a minimization problem. In this case, we're going to actually formulate it as, instead of a summation of the wire length, it's going to be a summation of the squared wire length. Now, why squared? The only reason is a squared function has a minimum, right? You think of calculus, x squared, it's convex. If you can find that minimum, it's good. If you have just x minus y absolute value, that's actually a linear function, and actually it's not continuous. That's hard to optimize. So linear functions are hard to optimize, whereas this quadratic of the wire length can be minimized quite well. So what do we do? The best thing is a toy example. So we're just going to do one dimension. We're going to do the x dimension. When you do a placement, you actually do x and y. They're done simultaneously. They're independent problems because if you have a bounding box, you minimize the width of the box and the height of the box at the same time, right? They're kind of, the width is a function of the x locations and the height is a function of the y locations. So they can actually be done separately. But in this case, we're going to look at this x dimension with two IOs and two cells. We're going to assume that one IO is fixed at a distance of 100, one IO is fixed at a distance of 200, and those two cells are at x location 1 and x location 2. They're movable. Where do you put them? Well, what this does is, in this case, it's going to have the same wire length, in linear wire length, right? It's going to be 200 minus 100. The wire length will be 100. But that's not always the case with nets. And also the squared wire length will not be minimized for that because you actually want to balance the maximum wire length too, right? So this is not the minimum squared wire. Any placement gives you the minimum linear wire length, but any placement is not the minimum squared wire length, is my point. So we formulate this as a cost function where we know x1 is connected to this location over here, and so that distance, or this wire length, corresponds to this over here. It's x1 minus 100 squared. That's the length of that first wire segment, squared. We can then do this wire segment is formulated as x1 minus x2. It actually doesn't matter which direction you do it. It could be x2 minus x1 squared, and it corresponds to this middle part. Because squaring it gets rid of the positive and negative, right? So it doesn't really matter. And then the third component is this wire length, which is 200, x2 minus 200 squared, and it gives us this component. So that cost function is the total of the squared wire length in this design. Now, what do? Well, we can basically take the derivative of it. And again, this is supposed to be derivative, partial derivative sign. We take the derivative with respect to x1 and the derivative with respect to x2, and we set those equal to 0. If you remember back to your calculus, that'll give us the minimum value for this equation. So what is the derivative? Who thought they'd never use calculus again, right? But we're using calculus again. And the derivative is quite straightforward, right? You take the exponent, put it in front, minus 1. So the derivative of the first term is 2 times x1 minus 100. The derivative of the second part is 2 times x1 minus x2. And then the third term, because we're doing the derivative with respect to x1, the third term is a constant. x2 minus 200 is a constant. So you don't include it in that partial derivative. Same thing for the second one, except the first term is a constant, gets dropped off. Then you have the exponents for those. So set those equal to 0, and we come up with a placement. Now, the nice thing is that can be done as a matrix operation. And you can actually don't have to do those partial derivatives all the time. You can actually set it up as a connectivity matrix where the IOs are part of this B vector. And then the cells are actually part, this other vector right here, this is something that's called the Laplacian. And you basically just fill that in from the connectivity of the design, and then you solve this for x1, x2. So you're solving a linear system. So that's why we did the squaring, because we have a linear system where there's basically one solution now, and there's actually provably one solution that's the minimum that will give us the minimum value. So super convenient, pretty fast. It gets you the same solution all the time. Like if you repeat it with the same netlist, it'll give you the same solution. And so now, why formulate this way? Well, because we can, and it's trivial to solve. It's a study of linear systems. There's only one solution. The solution is optimal. The solution, now it conveys relative order. You actually have a placement, but we're going to show that it's actually not a good solution. Now, what do I mean by that? Let's look at what an actual solution to something looks like. So I'm going to skip over this. This is the original paper that did it. But this is what a quadratic placement looks like when you do it. What's the problem?
Small amount of overlap.
There's a little overlap in there. So it's not good in that regard. There's no overlap constraints at all. Right? Partitioning's good. Put them in two separate groups, they can't overlap. Here, which one, these two cells up here, you know that one of them should be kind of to the left of the other and a little bit below, but they overlap. So what do? Well, the actual approach is to do partitioning and quadratic placement. This is what most of the algorithms do. You remember how I said during partitioning, the seed placement, how you start the partitions affects the result of the partition. Well, here we're going to use quadratic to seed the partitioning and then partition. So basically, do a quadratic placement, you have a bunch of stuff overlap in the middle, now bisect it. Then the Gaussian algorithm, which I just gave you the reference, says, now do the same thing like the recursive partitioning, except do a quadratic placement of the left and a quadratic placement of the right, but maintaining that their center of gravity is in the middle of those two partitions. And you can actually, another way to think about it is if there's something cut here, you can basically make a pin, and you can also freeze it on this perimeter. So like you do in the other pins, right? That's another way to do that rather than forcing a center of gravity. But Gaussian did that. And then you place them in those regions. And then you can basically partition it again, right? Then you do a horizontal partitioning. Repeat. A lot of algorithms do this. And this gets pretty good results. Yeah. Now what are the pros, cons? Well, it's mathematically well behaved, it's efficient to solve, it has good quality. That solution, it's not a legal placement, but it's a good seed to partitioning. So if you do them both together, it's pretty good. Now the one con is you actually need the IOs. Because if you think about it, the IOs kind of spread the design apart. If you give it a bad IO placement, you get a bad placement. Right? You want to spread it apart in the right ways, not the bad ways. So that's why your IO placement I mentioned is always a problem. Fix your IO placement. That's the number one thing to solve get a better placement. And this is why, because when you're doing quadratic type placements, it pulls your design apart. And you want to, let's say you have a bus, bit 0 and bit 1. You don't want bit 0 to be in the left upper corner and bit 1 to be in the lower right corner, because what if something's connected to both of those? It gets put in the middle of the chip. That means you have a bad quadratic placement, and it starts your partitioning bad, and you end up with a bad solution. Now, there's one other solution here. So I really like by partitioning, because it's a simple algorithm. There's another simple algorithm called stimulated annealing. This is a set of what are called stochastic optimization algorithms. What do we mean by stochastic? They're based on probability. it actually goes back. It's called simulated annealing because it's based on simulation of the annealing process. Now, what is annealing? Blacksmiths used to make swords and things. And how do you do it? You heat metal up, you form it, and then what you do when you want to make it really strong is you want to actually cool it down very slowly. The best armor, the best swords. Is anyone do blacksmithing? No? Yeah? Well, if you cool it down at a regular level, it basically lets the metal form a perfect lattice so it's stronger. Right? The best blacksmiths will do it in a carefully controlled way to get the strongest material.
Also glass.
Also what?
Glass making, and
Oh, glass making too. Yeah, glass too. And remember chip making. When we did ion implantation, we had to anneal it to smooth the surface. Same idea. So it borrows from this idea, except we do it in kind of a simulated way. Now, what do we mean? Well, think about placement. What we're going to try to do is start with X locations and row assignments of cells, and we want to basically, these could be the bins for global placement, they could be the actual locations in the rows, it could be formulated in a number of ways. But basically you want it so that you can formulate any problem as a set of these placements in our solution space. And then what do? Well, you want to come up with a set of moves. And a move might be take one cell and move it to a new location in a different row. What location? It could be random. Pick the next row, put it anywhere in the next row. Or another move could be take two cells, swap them. Why might we want to do that? Well, maybe it improves both of them at the same time. Or we could have another example, M3. What if we change the orientation of a cell? We flip it horizontally, or I guess our rows are usually in a fixed vertical orientation, but we might want to flip it horizontally. Because maybe that means the pin on the left is closer to where we want to be than the pin being on the right. Now, if we take, these are kind of neighboring solutions to a current placement. Or in other words, it's an iterative change from the existing placement. Now, what does simulated annealing do? Well, the top level algorithm says pick one of those moves with a certain probability. What we're going to say, we might pick, and I'm just going to say, we might pick move 1 with 4/5 of the time and M2 with 1/5 of the time. Maybe we start out, we don't even want to pick M3 because it's kind of a local change. And so basically, 4/5 of the time we just move a cell randomly, and some of the time we swap cells. But then we might also have some other restriction, like how far do we displacement or something. But it's basically a set of rules that we randomly pick, and we apply the rules. Now, what do we do then? Well, we're going to actually have what's called an annealing schedule, and this is going to mimic the temperature as a blacksmith cools something. And what we're going to do is, when it's a higher temperature, we want to do riskier moves. We want to try crazy things. When you get to cooler temperatures, you want to do less risky things, and you want to kind of ensure that it will make improvement. And the temperature depends on, it's also a heuristic. This whole thing is a heuristic, but I'll conclude later. But depending on the number of modules you have and some constant, you just geometrically decrease the temperature over time. It's called the annealing schedule or the cooling schedule. Now, what do you do at each of these temperatures? Well, you pick a random move and you try it. Now, I forgot to add a slide on. I didn't add the slide in here. But I should have a slide in there is, this temperature, you don't always accept the move. You actually accept it with a certain probability. So if it improves your design, you might always accept it. But if it makes your design worse, sometimes you accept it. Now, why is that? To get to a good solution, sometimes you have to pass through bad solutions. And in this temperature schedule, what this does is says, this is directly related to the probability that I'm going to accept a bad move. And I should have the temperature, the probability is going to be related to an exponentially decreasing temperature. Right? So as the temperature goes down, actually, I got it backwards. As the temperature goes down, when the temperature's high, when the temperature's high, you want to take moves with a high probability, and when it's low, you want it to decrease the probability. And so you basically start out doing crazy stuff, and as you cool it down, you do more and more conservative moves until you get to the final temperature. Now, if you do this long enough, it's been proven that you will converge to an optimal solution. You will. Now, how do we measure what is the correct value? Well, you have to have some cost function to say, is this one better or not? What can it be? Well, how about wire length? Let's just say, is the wire length better? Then it's positive improvement. In this case, it could be horizontal and vertical wire length, the HPWL. So HPWL. Another cost function could be, do I have overlaps in my rows? If I have overlaps, that's bad. It's not a legal solution, so I might want to spread things out. Or it could be, do I have too many things in some rows than other rows? If I want to even out my rows, that'll kind of minimize my cell density. Yeah.
Is the temperature just solely based on the number of iterations you've gone through?
The temperature, so generally what you do is you decrease the temperature exponentially and you do a number of iterations at each temperature. Like you might do 5,000 moves at this temperature, decrease it. 5,000 at this temperature, decrease it. Yeah, that's a good question. So you got any of these cost functions. Now, the nice thing about this is you can actually add any cost function you want. But the bad thing is how you combine the cost functions. How you trade off wire length versus overlap. I don't know, by the end you want no overlap, or what about row length? By the end you want even rows, but if I make them a little uneven for less wire length, is that okay? Depends how you weight them. So it's quite heuristic in how you define the costs. So the nice thing about simulated annealing, any cost can be handled. It's easy to get to an optimal solution, but it's slow. It doesn't scale to millions of cells. You can do it for 5,000, 10,000 cells. It can actually do quite well. The other negative thing is you have to tune the move probabilities and the types of moves and all this stuff. That takes time. That takes benchmarking. You have to try it. So it may not be the most efficient thing. Yeah.
You mentioned scaling the cost functions. When you say you, who is that?
Oh, when I say you, it might be that's a good question. It might be an input to the tool. There's probably some default values, but you might want to change them for your design, right? Because maybe your design is heavily wire length dominated, so you want to penalize that more than row length or something. Yeah.
Would we be able to define our own cost functions as well, or is it a preset?
Can you do your own cost functions? Maybe. I'm going to say I don't know any. I know one commercial tool that does simulated annealing these days. It's actually, I skipped over the slide, but there's two original papers. It's called Timberwolf. This is by a guy, Carl Session. He's at Yale now, and another student of his, Bill Schwartz, who was at Yale as a PhD student. He's a friend of mine, actually. They did this research in kind of the 80s, 90s. None of the major EDA companies use simulated annealing, but I know Bill has a company called Timberwolf Systems that licenses to companies like Intel. Now, why does Intel use it? Well, Intel does a very hierarchical design where they have a block that they might optimize that's like 5,000 gates. So they do this. They may be slow, but they can optimize the hell out of 5,000 gates rather than placing their entire chip at one time. So they have a different methodology that lends towards this. Does NVIDIA do this? No, not that I know of. Does AMD do this? I don't know. Maybe. AMD might just do standard cell blocks and try to optimize those with traditional tools. I'm actually not sure. So this is an example of a tool that is there, but it's not very popular. Bill kind of maintains it, Intel licenses it, and so on. Yeah, it's mostly so you can be aware of kind of these techniques. Also, simulated annealing, if you have a problem you want to optimize, this is a good approach to use for anything. you just have to decide what is my solution space, what are my moves, and then tune the probability and temperature schedule. There's actually Python packages for simulated annealing that you can just make functions that do those things and then give it to the Python library. So, and I will say there's a whole bunch of other stochastic optimization techniques. What are some of them called? There's like simulated annealing. There are genetic algorithms. They do the similar thing, except you try to model it as a population, and each individual in the population has a set of chromosomes. And then they basically breed, and then you have survival of the fittest. So you try to model it as evolution. But it's the same idea. How do the parents combine to form a child? That's the probabilistic part. Does it survive? That's another probabilistic part. But it's the same type of idea that if you have a population that's big enough over time, it'll get to a good solution. That's not done for placement that I know of, but it could be. Are there gradient descent algorithms? There are. Those are kind of related to quadratic placement, right? Because quadratic placement gets you the minimum. There are some, but what do they do? You have to find another way to spread things out than quadratic placement. And so one other approach can be to add a term to penalize overlap. So then you want to minimize wire length, but kind of not have the overlap. I think Gordian might have done something like that too. Now, what do our tools do? Well, our tools, actually there's replace, and then I think they might have replaced it. But there's actually some interesting demos. And let's open this in. They have some interesting kind of animated GIFs down here somewhere. Actually, where'd it go? Let me find this. Oh, there we go. Let's get over it. This does like a set of, it's basically, well, if it starts up again. This has a floor plan of the blocks, and it does basically quadratic, but it has some extra terms to like distribute the center of gravity. So you can see like these pockets kind of move things around. And so this is kind of iterations over time of this benchmark.
Wait, what are the red things?
The red things are the cells. The blue blocks are your macro blocks. The red things are your cells, and you can see things. Right, again, that takes a long time to compute. That's trivial to show it that short. This takes like hours to run. This design, I don't know. Actually, maybe minutes for this design, but here's another.
What were the two algorithms? There was one called FIT and another one that was two names.
Fit.
Nesterov and then the first, and then at the very beginning it said a different one.
I don't know what you mean. Here's another benchmark. Yeah, I think this model is basically the white space, I think, is the other cell. So you can see kind of pushing stuff into other regions. But you can see kind of the pockets of the connected things sticking together, right?
Looks like oil in water.
Yeah. Question? Oh, that's okay. It's awe-inspiring, right? Yeah. So yeah. Does it cause issues if it leaves empty space? I mean, it's wasted space. The issues would be you're paying for silicon area you don't use.
Would it help with congestion if that empty space was more distributed throughout the whole design?
That's a good question. And there's not a concrete answer. Is it better to distribute that white space or not? What are the trade-offs? Well, it would improve routing to reduce congestion. But it would negatively affect power. Right? If things are spread out more, all of your wires are longer, your power goes up. So I don't know. Maybe. There's not necessarily one answer. It might affect your timing then too. So it depends on the design. This is where LLMs can't replace us yet, right? So yeah, there's maybe a couple others in here. I don't know what this is.
Yeah, FIT and then Nesterov.
Yeah, I don't know what this example is. Nesterov is the algorithm they use. It's a way of iterating, as far as I remember, it's a way of iterating with kind of the center of gravity constraints to spread out the quadratic more rather than using partitioning. Because you can see they basically come up with the center of gravity coordinates that are what spread it out. So it's not using partitioning. Yeah, I don't know what's the other one. I don't even know what this is. Oh, that's a demo. Okay. So anyways, so that's an example. Now, what are the options you can use in the tools? Well, there's a few things. What did we talk about before? How much area do you have and where are the IOs? In LibreLane, OpenLane, there's two ways of deciding how much chip area you have. The default is to do what's called relative sizing, which means it'll take the summation of how many gates you have in their area, and then you give it a utilization. Let's say you give it like 50% utilization. What that does then is say, if your cells are 10,000 area units, make my floor plan 20,000 units, so that my cells are 50% of my area. Then pick the aspect ratio. Is it square or whatnot? By default, it'll just make it square. So relative and utilization ratio is basically the simplest way of doing it, and will make something that probably will work, maybe will work. You can also pick a fixed area. When you do something like tiny tape out, you're given a size. You can't decide an arbitrary area. It's an absolute dimension with a fixed floor plan and a fixed aspect ratio. Or in the capstone, we're using the wafer space templates. Those are fixed. So that's one thing you can do is how do you determine the area of my chip to put stuff in? And these are all variables that are basically in your config script that control this during placement. So you set these all caps variables. They change over time. The usage in OpenRoad has changed. These might even be a little outdated. I haven't played them that much recently. Then you can also have like the pin ordering file. This is basically which side the pin goes on, and then you can, so northeast, southwest, and then how you space them out. Do you want them equally spaced? Do you want them to be able to slide around on a side? What do you want? I actually wrote a script that put them in a fixed order on mine at a fixed location that was kind of equidistant. But there's ways of replacing it on your own if you have reasons. So those are the floor plan options. Now, what about macro options? By default, it'll place your macros with another algorithm, the big blocks. You can define the halo, how much space to leave around your blocks. Actually, they used to have an option called the macro channel. I think they got rid of this. The halo is also the channel. The channel is basically if you have two blocks, you could have a different distance between blocks rather than around the entire block. But I think halo is the one for both of them now. You can also have a fixed placement of all your macros. Now, what I recommend for this type of thing, if you're doing a big design, is you can run through your placement. You can actually get your floor plan, and rather than redoing macro placement every time, you can actually freeze it and say, keep my memories at certain locations, even when I change my design. This might speed up your iterations so you can get to a solution faster. So I recommend you do that. That can also work. I guess it's also deprecated, but there was something else that was similar to it. I forget the name. It also depends if you're using LibreLane or OpenRoad has their own set of flow scripts, and Tiny Tape Out might be a little different, but these kind of same options exist in most of them. There's also a bunch of kind of options for the placement of the cells. First one is target density. Now, this is different than utilization. So utilization is at the floor plan level and says, I have 50% of my chip is cells. this says how much do I spread it out. You asked, is it okay that I have kind of this part of my chip that's empty? If I had a spread target here, that'll say don't leave that white space. So this is what you can actually tune to get that placement. By default, dense means don't even worry about it. Leave space in an area. You can also do routability or congestion-driven placement. You can do timing-driven placement. You can penalize wire length more or less in your cost function relative to timing-driven and congestion-driven. And random global placement is another one that you can kind of start with if you don't want to have consistent results, but maybe explore other solutions. And then there's one other thing for like legalization distance. This is basically when you make changes like gate sizing, you want to move a gate to fix it. This is how far it can move from the original location. This was actually an older version. This was something we had to do to be able to sometimes we would put a clock buffer, for example, in the middle of a macro, and then it wouldn't be able to move it to a side of a macro without changing this default value. But these are the types of things that you have to look into the placer and see, what can you control to get the results. And then resizer, this is when you do timing optimization during placement, so buffering, sizing, and so on.